This is our last lesson in Unit 7. We're going to look at logistic growth for BC Calculus. We're going to discover that there are 4 types of differential equations that we're responsible for in Calc BC. The first 2 types we covered in AB Calc, and those were position, velocity, acceleration, and then simple growth and decay. We're going to see logistic growth in BC, and we're going to see either this form or this form. So first of all, let's solve the logistic differential equation where K and L are positive constants. So if we take this to be, let's see, I'm going to kind of rewrite this and say Kp times L minus P divided by L. We can get that common denominator there. And then we could say dP divided by P times 1 minus P over L is equal to K dt. So I'm separating the variables from this step here, dividing by P and 1 minus P over L and leaving the K on the right. So we separated the variables. Now we're going to integrate both sides. So we have 1 over P times 1 minus P over L can be rewritten to be L over P times L minus P. And that can be 1 over P plus 1 over L minus P. Back up here, we need that to be a 1, not an L. Getting ahead of myself again. So switching colors, we have dP over P plus dP over L minus P. So I'm taking this to be my left side, and the right side is going to be K dt. So integrating this, we have natural log of P, and this is going to be minus, since that derivative is going to be -1. Natural log of L minus P, and this would be KT plus a constant. So we got natural log of P and natural log of L minus P times the derivative of P, -1, and then KT plus C. So using properties of natural log here, we have natural log of L minus P divided by P, and I'm going to put that negative on the other side to be negative KT minus C. So if we exponentiate both sides, we're going to exponentiate, we'll have L minus P divided by P is equal to e to the negative KT minus C. So L minus P divided by P is, and I'm going to say, if we have e to the negative KT and e to the negative C, I'm going to call this capital A because it's just some other constant. So I'll have A times e to the negative KT power. And then solving for P, we'll have L divided by 1 plus A e to the negative KT power, which was, I believe that was our equation right here. So we just took this form and we solved it for that form. So the parameter L represents the limiting value or the carrying capacity. The parameter K represents the relative growth rate, where when P is small relative to the limiting value. And the parameter A depends on the initial condition, P sub naught. So some important facts of logistics functions is the idea of the carrying capacity, capital L. We say that this is the maximum population that the environment is capable of sustaining. It's the maximum population that some environment is capable of sustaining. So you might have heard of this in biology. So as P goes to 0, then the derivative is going to go to K times P. But as P approaches L, then the derivative, the rate of change of the population, is going to get close to 0. And we'll see that here in a minute. So here's a graph of the function P. This is called the logistic curve, that little S-shaped curve. The logistic growth, the population grows the fastest when the population is half the carrying capacity. So if we scribble on our notes here, this is my carrying capacity, or the limiting factor. That asymptote, that's the most that the environment, the biggest population that the environment can sustain. And this piece is concave down on this part and concave up on this part. And right here, halfway, is the maximum slope, or that maximum rate of growth at the point of inflection. And we're approximately exponential right in here, you can tell. So the graph of the function is called the logistics curve. And in logistics growth, the population grows the fastest when the population is half the carrying capacity. So that's where we're growing the fastest. The maximum value, for some reason my pen is running behind here. The maximum value of the rate of change of population with respect to time is going to be when the population is 1/2. And to find the time of the maximum rate of change, we're going to use the formula 1 over K times the natural log of A. I think I'm going to turn off the calculator because it's causing me to go slow here. Let's see if that helps a little bit. Yeah, that's better. So to find the time of the maximum rate of change, we're going to use this formula. 1 over K times the natural log of A. The slopes are small near P equals 0. And if you go back and look at your graph, you can see that. And they're small as the population equals the carrying capacity. And they're steepest around the point of inflection, which is going to be half of the carrying capacity. And what happens if the population approaches the limiting factor? Then our slopes are going to be negative. And the population is going to be decreasing. If the population is bigger than the carrying capacity, the slopes would become negative and the population would begin to decrease. So let's put all of this together and give this a try. You need a calculator. So a population of coyotes in a wildlife preserve is modeled by a logistic function, and the preserve can support no more than 100 coyotes on the property. And we want to write the differential equation with our K value being 1/10, where T is measured in years. So we can say the differential equation would be the rate of change of the population with respect to time is the K factor, so 0.10 times the population, And we've got 1 minus the population divided by no more than 100. And if we simplify this, let's see, we can put this as 100 minus P. If we pull out the 100 here, and that would be 001 times P. So here's the slope field shown at the right, and we want to know where the horizontal asymptote would appear to occur, and that would be right here at y equals 100. That would be y equals 100, which would be our carrying capacity. So what happens if the initial population is above this asymptote? Then that would mean that the population is in decline and overpopulated for that particular preserve that's supporting the animals. We want to be able to draw that curve. So using our calculator, see if I can get this on here. We had 0. So let's go find the general solution. So we'll graph the graph after we find the initial solution in part E, I believe. We'll come back and graph the graph. What happens if the initial population is above the asymptote? Well, we said that the population is in decline. The population is in decline. It would be overpopulated. For the preserve. And if the preserve initially begins with 20 coyotes, we want to sketch a graph of the population on the slope field. So just looking right here, if we started at 20, then we could make an estimate. We want follow that slope field, something along those lines. So we have some kind of an estimate here with 0.20 being our initial value. And now we want to find that general solution and the particular solution if we started at 20. So the general solution, the rate of change of the population with respect to time, was our formula we started with in the first part. And we want to integrate, so dp, and we're going to divide by p, and then I'm going to get this as a common denominator, 100 minus p divided by 100, and that would be 1/10 with respect to time. So again, separating this into two different parts, I believe we're going to have to use partial fractions here. So dp over p plus the integral of dp over 100 minus p is equal to 1/10 dt. So let's think about this for a second. We've got this step, we need partial fractions. So we've got 100 in our numerator divided by p times 100 minus p. Those are our two factors. And we've got a over p and b over 100 minus p. So if we have 100 here, we've got a times 100 minus p plus b times p. So if p is 100, we'll kill this off. If P is 100, then we have 100B equals 100, so B is 1. And if P is 0, then this is eliminated, and we have 100A equals 100, so A is 1. So back here we have a 1 here and a 1 here. And then going back to our problem, this is natural log of absolute value of P. And then we've got natural log of 100 minus P times the derivative of negative P. So that's negative natural log 100 minus P. And this integral is 1/10 of T plus a constant. So again, we want to exponentiate both sides, this side and this side. So we have 100 minus P divided by P, and I'm taking this negative and putting it on the other side. So we have e to the negative 1/10 T minus C, and we're going to let e to the negative C represent as A, just a constant. So 100 minus P divided by P is equal to A e to the negative 1/10 T. And then they want us to let P of 0 represent 20. So if we put 0 here and 20 here, we're going to end up with the A value as 4. So we have 100 divided by P minus 1 is equal to 4e to the negative 1/10 T. And you see where I got the minus 1? I pulled this fraction apart. So solving for P, we have P is equal to, doing this in my head, see 100 divided by 1 plus 4e to the negative 1/10 T. So here's my general solution. And if we go to our calculator and graph that out, you're going to see the graph that looks like this. And I believe if we look at the, if we control table, look at the table, you can see at 0 we have 20. So this is going to be our graph. We'll go put that back on our graph paper in just a second. They want to know, when will the coyote population reach 80? So we could do that algebraically. When 80 is equal to 100 over 1 plus 4e to the negative 1/10 T. And 80 divided by 100, let's see, that's 100 divided by 80, that's 5 over 4, is equal to 1 plus 4e to the negative 1/10 T. So 5 is equal to 4 plus 16 e to the negative 1/10 T. And see, so 1/16 is e to the negative 1/10 T. So taking natural log of both sides, we got natural log of 1/16 divided by negative 1/10 is our T value, and using our calculator to estimate that, we've got 27.7258 years. So we have a coyote population of 80 at 27 years. So let's go back to the graph. I'm going to go back to the original one. So at 27 we have 80 population, 27.73. The population is 80. And then on part G, when will the coyote population be growing the fastest? Well, we said that was half of the limiting capacity. So that would be when the population is L over 2. So that would be 100 divided by 2. So when the population is 50, and we can again substitute into our formula. So T is 1 over a 10th natural log 4. And on my calculator, that looks like about 13.862 years. And to answer part H, the limiting factor as t goes to infinity is going to be 100. So going back to our graph, we know at 13.86 years, so 13.86 years, we're growing the fastest right at 50. And you can see we're following along that curve rather nicely. So 13.86, we have a population of 50. And again, looking at the calculator, gives us a better approximation right there. Okay, then our last couple. Let's see, I'm going to close this calculator up again. It's really slowing down my video feed. Okay, so the last type is Newton's cooling law. We said we're going to see 4 different types. Newton's cooling law can either be in this form or this form. And let's say, for example, you bought your favorite frozen coffee treat on the way to school at the drive-through window of Starbeams, and your car is always kept at a constant 65 degrees Fahrenheit. Traffic was terrible, and you spend 10 minutes getting to school. The drink warmed to 35 degrees Fahrenheit because you checked it with your temperature probe at the red light. So it's melting. Then 2 students had a rear-end collision, and another 10 minutes passed trying to get into the school parking lot, and you checked your drink again, and it warmed to 50 degrees. Use Newton's cooling law to estimate the following. What's the frozen coffee's original temperature? So we want to first say dy dt is k times y minus the initial, which was 65 degrees. So if we integrate both sides and separate the variables, then dy is y minus 65 and k dt. So we have the natural log of y minus 65, and that's equal to kt plus a constant. So exponentiating both sides, and again using those properties, if e to the kt times e to the c, we're going to call e to the c a, where e to the c is a. So we have the natural log. E to the natural log is going to give us y minus 65, and that's going to be a e to the kt power. So moving the 65 over, we can say the general form is a e to the kt plus 65 degrees. Now, we know already from the beginning, we know that when it was 10 minutes, what is going on there? Wow. We know at 10 minutes, so the y of 10 was 35 degrees, and then the y of 20 was 50 degrees, so it got cold and then it got hot. Okay, so we want to substitute those values in. So that would be the next thing. So by substituting, we can find that 35 minus 65 is equal to AE to the 10K, and we know that 50 minus 65 is equal to AE to the 20K. So we could say that negative 30 is equal to AE to the 10K, and negative 15 is equal to AE to the 20K. So if we divided those together, then we could say that 2 is equal to E to the negative 10K, because that would eliminate, and the natural log of 2 would be negative 10K. So our constant would be negative natural log of 2 divided by 10. And if you think about this, negative natural log of 2 would be the natural log of 2 to the negative 1 power, or the natural log of 1/2. And next we could use our formula for our K value and say y is, let's see, what was our formula? AE to the KT. So our KT is negative natural log of 2 divided by 10 times the time, which was 10, plus 65. So y was 35 at 10 minutes. So 35 at 10 minutes. And 35 minus 65 is negative 30. And this 10 gets rid of this 10, and we have A to the 1/2. So A is negative 60. And that was at the 10-minute mark. So to find the original, we want to go back and say y is equal to negative 60 e to the kt power plus 65. So the y of 0, substituting 0 for our initial, since this is a, we got negative 60 e to the 0 times the k value, so that's going to all go to 1, plus 65. So initially, that was a hard bit of algebra. Initially, our favorite frozen coffee drink was 5 degrees Fahrenheit, so that's frozen, solid frozen. It's like a brick. This sounds like a math book problem. It doesn't seem very realistic. When would the drink reach a temperature of 63 degrees? Well, we could use our formula. Y is negative 60 e to the negative natural log of 2 divided by 10, negative, times T plus 65. So we want to know when the temperature is 63. Negative 60e to the negative natural log 2 over 10 t plus 65. So we're going to solve for t. So subtracting 65 from both sides and dividing by negative 60, we got 1 over 30 here, and natural log of 2 over 10 to the t. So if we're taking natural log of both sides, we got natural log of 1 over 30, and that's equal to our exponent because natural log cancels the e, and we have negative natural log 2 divided by 10 times the time. So our t, again, grab out your calculator. We got negative 10 divided by natural log 2 times natural log 1 over 30. And when the time is about 49 minutes, the temperature would reach 63 degrees. So about 49 minutes, the temperature is 63 degrees. What would the temperature of the drink be after 1 hour? Well, that's pretty easy. Our time is in minutes, right? So we got negative 60e to the negative natural log 2 over 10 times 60 minutes plus 65 to start off with. So this 10 divides that 60 6 times. And using our calculator, it's about 64 degrees after an hour. Let's see, there is an alternate method. I should mention that. You can solve for K. Let's talk about this. I'm going to write the notes down here. You can alternate method to solve for K. And we could use y equals ae to the kt plus 65. You just plug in both points, plug in 1035, and then plug in 2050, and solve for a. And you're going to end up with two equations, negative 30 over e to the 10k and negative 15 over e to the 20k. Set those equal to each other, solve for k, and to me that would be quicker than all the stuff we did. So that's the end of chapter 7, ladies and gentlemen. See you in chapter 8.